Okay, I'm recording this because if you are out, I want to make sure you don't miss today's lesson. And even if you were here, if you want to listen to it again, this will really help. Because this chapter builds on itself. It gets a little tricky at times, but if you follow it step by step, it's not too bad. What we're studying is analytic trigonometry. And what I consider analytic trig to be is the logic part of trig. It's like doing logic problems and so forth. And if you like doing logic problems and solving and making things work out, you're going to love this section. I'll try to make it as painless as possible, but yeah, it gets tricky on parts, but you need to just pay attention. So yeah, it's close to proofs. Yeah. So the first thing I want to show you is some what they call identities. Now, before I go forward, let me remind you of kind of the basics. We defined the sine of theta originally as SOHCAHTOA, opposite over hypotenuse. But when we got to the unit circle, and it's the unit circle definitions I want to stay with, we defined it as y over r. It's just like opposite over hypotenuse, but it's the y coordinate over r. Cosine theta is x over r. Tangent theta is y over x. And then we just defined the reciprocal functions, and we defined cosecant, abbreviated CSC, of theta as the inverse, or the reciprocal. It's y r over y. We defined secant as r divided by x, and bless you, and cotangent as x over y. Okay? Any questions about those? So those are the basic kind of definitions of the ratios that we were looking at. Yes. Now, the identity functions, I'm going to extend this page down, fall right out of those definitions, and it sort of makes sense that the sine of theta is 1 divided by the cosecant of theta. You just flip it upside down, and the cosecant of theta is 1 divided by sine of theta. I think it's pretty obvious if you do 1 divided by y over r, you get r over y and vice versa. And we can extend these on down. Cosine of theta is 1 over secant theta, and secant theta likewise is 1 over cosine theta. And finally, tangent theta is 1 over cotangent theta, and cotangent theta can be defined as 1 divided by tangent theta. Just to give you an example of these, if you happen to know, for example, that the sine of 30 degrees is 1/2, I can use these identities, shrink that down, to tell you that the cosecant of theta is 1 divided by 1/2, or exactly 2. It's just the reciprocal. And that's all those identities. So those, I think, are fairly straightforward. Question, Maggie? Mm-hmm.
Why is it 1 over? Like, why do you put 1 over?
Okay. Let's just do the math on it. If you agree that sine is y over r, then what is 1 divided by y over r? How do we do fraction division? Flip and multiply, right? So that would be 1 times the reciprocal, which is r over y. Of course, 1 times r over y is r over y. And we just said that is the definition, if we go back, if we go back up to the top, of cosecant. They pair up. They are reciprocals. Y over r over y. This covers all 6 ratios that you could possibly have with 3 sides. We put every one of the possible 3 sides in the numerator, paired up with every one of the remaining 2 sides as the denominator. So there are 6 different ratio combinations, and we just give them all names. Now, there's a reason why they're named what they are, and I'll explain some of these tomorrow and the next day. And I can actually explain how tangent in trig is related to the idea of tangent with a line that just touches a circle at one point, but or intersects. But I don't want to go there today. So those are the basic identities. Questions? All right. Now for one that's a little trickier, And I'm actually going to prove each one of these to you as we come to it. The tangent of theta, you may have already figured this out, but it is equal to the sine of theta divided by the cosine of theta. And as a proof, you know that the sine of theta is y over r, and cosine of theta is x over r. So when I take y over r for sine and divide it by x over r, again, I've got fraction division, so reciprocal. Exactly. You flip and multiply, you'll see that you get y over x. The r's will cancel out. Because you have y over r times the reciprocal r over x. The r's cancel, leaving you with y over x. And the definition of y over x is tangent. Nope, don't have to be able to prove it. You need to know this identity. But you should actually be able to prove it just based on the steps that we followed. If you just plug in, what is the definition of sine? It's the ratio of y over r. What's the definition of cosine? X over r. If you just simplify that fraction, you get y over x, and then you should know, oh yeah, that's tangent. And it shouldn't come as any surprise then that cotangent, which is the reciprocal of tangent, is cosine over sine. Exactly. Because it's x over y, not y over x, and it works that way. Now I want to show you that it really works. So give me your favorite number between 1 and 90. 47.
71.
All right.
47.
All right. Let's say the tangent button on your calculator is broken, and you can't go tangent 47 to say that it is 1.07236871. Just hold that number for a second. What you can do is take the calculator and find the cosine, or I'm sorry, we're doing tangent, clear, sine of 47, and divide it by the cosine of 47. And when I hit the enter key, you'll see that you get exactly the same number. It's got to work, right? Because if it doesn't work, well, then it's wrong. Now, I want to skip ahead. When is this useful? It turns out when you get into calculus, you're going to do things like find the integral, which is like the area underneath a curve. And you might find the area underneath a tangent curve. And it turns out you can't immediately use that, but you'll learn in calculus that if you convert tangent to sine over cosine, you can do things like take the integral of it. So it's a long way of saying you're going to need this in calculus. Will you ever need it in life?
No.
Very unlikely. I've been in some high-tech fields, and I've never converted tangent to sine over cosine. But it's also kind of neat for logic, and it will be used on the ACT too, so another reason to use it. All right. Y'all ready to go to the one that I think's it's kind of like the granddaddy of them all? Oh, that'd be a lot. If we have a right triangle, and we just label the sides y, x, and r, and that's theta, okay? You already know from the Pythagorean theorem that x squared plus y squared equals r squared. It's just, instead of a, b, and c, I just said x, y, and r. And I chose x, y, and r for a reason, because those are the designations we use when we're dealing with the unit circle or any circular trig function, actually, for that matter, with a radius r. Okay? So far, so good? Mm-hmm. All right. I'm going to show you what the Pythagorean theorem for trig looks like. Shimmy, have you had this before? Oh, so you know what's coming. Do you want to tell everybody what I'm about to write?
Pythagorean theorem.
This is the Pythagorean theorem for trig. Sine squared, oh, I put x, I'm sorry. I meant just theta. Let's keep it clean. Sine squared plus cosine squared equals 1. Now, I've got to show you something that you haven't seen before. When we talk about sine squared, this is really what I mean. I mean, find the sine of theta and then square it. But in trig, we don't write it that way. We'll often put the 2 right above the sine And that means what I wrote in blue. And likewise, this is the same thing as cosine squared. And actually, I read this as sine squared of theta plus cosine squared of theta equals 1. Now, that's pretty cool when you think about it. Again, give me another number between 1 and 90, and I'll show you that it works, and then I'll prove it for you. 71. So we go in and we take sine of 71. So I'll go sine 71, and I'll actually square it. And then I get a number. And then I do cosine 71, and I'll square that number. And I get a number. And if you look carefully, you can see that those two numbers add up to be exactly 1 every time. Yeah. Go ahead.
They just write it as sine theta squared instead of sine squared theta.
Right, what I wrote in blue?
That's weird. Yeah.
That is a good question because to me it's much clearer that way. And the saving of two parentheses marks hardly seems worth it to me. I think that's much clearer, but they don't. And since no one does, you've got to get used to that, the way they write it. So, Laura, did you all already have this in Spain too?
Yeah.
And you all write it the same way with the 2 right there, and then, yep, that's the way they write it all over the world. Okay, I want to do a proof. I want to show you that this works. So, we have sine squared. What is sine squared? Well, it is y over r quantity squared, right? And what is cosine squared? Well, that's x over r quantity squared. And I claim that equals 1. Okay? If we square it all out, we get y squared over r squared plus x squared over r squared equals 1. And that's convenient. We already have a common denominator. So we get, and I'll just put the x squared first, use the commutative property, and we have x squared plus y squared over r squared equals 1. And if you multiply both sides by r squared, you get x squared plus y squared equals r squared, which was exactly the Pythagorean theorem we started with. So this is really just the trigonomic way of saying, yeah. Well, you don't have to be able to do it, but just notice that it works.
Oh, yeah.
That sine squared plus cosine squared equals 1. And it works no matter where you are on any circle, but it especially works on the unit circle when you think about if you could be at the point 1, 0, and obviously 1 squared plus 0 squared is 1. You could be at the point 0, negative 1, and obviously 0 squared plus negative 1 squared is 1. I want to even show you that it works at other angles like 30 degrees. So if you go to 30 degrees on the angle, you may recall that the sine of 30 degrees equals 1/2. And the cosine of 30 degrees, if you remember on your unit circle, the x-coordinate that goes with it, square root of 3 over 2.
That's 35.
Square root of 3 over 2. Remember those?
Yeah.
Okay, so let's square them and see if they work. So I'm saying that 1/2 squared plus square root of 3 over 2 squared is going to equal 1. 1/2 squared is 1/4. Square root of 3 over 2. Well, you square root of 3 and you get 3. 2 squared is 4. And sure enough, it equals 1. It works. Okay, so we have time to do one more, and then I think I'm going to call it quits on this presentation. We'll do the others tomorrow. And we'll work, actually, I'm going to work one problem after this so you can see how all this can help you solve trig problems that you'll never see in real life. Okay. Here is another version of the Pythagorean theorem identity. One plus tangent squared of theta turns out to equal secant squared of theta. And you're like, you're kidding. You're adding a whole number 1 to some number, like some ratio tangent squared, and it's going to work out to be the inverse of cosine squared. And yeah, it is. So we do the math on this. I'll just work on the left side, and I'll show you how I end up with secant squared when I simplify it. What's tangent? Well, yeah, but it's sine over cosine, right? And since this is all squared, I can rewrite this as sine squared over cosine squared, right? since it's tangent is sine over cosine, but we're talking tangent squared, so we're really talking sine squared over cosine squared. Now, get a common denominator. That common denominator has to be cosine squared theta. And I'm going to rewrite 1 as cosine squared theta over cosine squared theta. So it becomes cosine squared theta. Now, did you see where I got that? 1 is cosine over cosine, cosine squared over cosine squared sine. Okay. Anyone want to take it from there? What's the top? Can't quite cross out. What's cosine squared plus sine squared? Pythagorean theorem. We just did it. 1. So all of this simplifies down to 1 over cosine squared theta. And 1 over cosine squared theta is the same as saying 1 over cosine theta quantity squared, because 1 squared is 1 and cosine squared is 1. Squared is cosine squared is obviously cosine squared. What's 1 over cosine from our very first identity? Secant. So it becomes secant theta squared, which is the same as saying secant squared theta.
How did we get rid of the secant?
We didn't. That's what it's equal to.
No, like, he's just proving it. Yeah.
I'm just proving that this does equal secant squared.
You're like the 1 over cosine.
Oh, 1 over cosine by definition is secant. Here, let me move this down. I've really got it kind of in. I simplified this to 1 over cosine theta quantity squared. And that's the same as secant. And so it all balances out, and that identity works. And I want to show you that. Now, we'll work a problem and see that it works. That's the easiest way. So I want to give you a problem that you know how to work from what you knew before you walked into the classroom today. And then I'm going to use the identity to also solve it. I'm going to tell you what tangent equals. I'm going to tell you the tangent of theta is 5. And furthermore, I'm going to tell you the cosine is greater than 0. Because remember, tangent can equal 5 if both cosine and sine are positive. It can also equal positive 5 if they're both negative. Okay? Now, in the old days, before today, you would work this problem like the following. You would say tangent theta is 5. So that's like the fraction 5 over 1, right? And that means TOA, opposite over adjacent. So I put a 5 here and a 1 there. Now that doesn't look proportionate because obviously my triangle's a lot skinnier and taller. But the opposite side would be 5 and the adjacent side 1 because we've got a tangent of 5 after all. And since cosine's positive, you know, it's positive 1, and that's actually what the triangle looks like. Now, you would probably then use the Pythagorean theorem, as Morgan says, this is square root of 26, and you would come in here and say, okay, based on that, sine theta is equal to 5 divided by square root of 26, and cosine theta is 1 over radical 26, and if you want to rationalize it, you can, and I'm not going to make you. So we're done. I want to do the problem a little differently, and you'll see that all of this still works. I'm going to use the identity. 1 plus tangent squared equals secant squared theta. Well, I know what tangent is. It was 5. And tangent squared is exactly what you think it is. It's 5 squared, it's 25. So I can replace this with 1 plus 25, and that's secant squared. And so 1 plus 25 is 26. And that's still secant squared. And if you want to know what just plain old secant is, just take the square root. Exactly. So secant theta is the square root of 26. Now cosine is what they asked for, not secant. But the cosine is 1 over the secant. That was our very first identity that we did. So we can now write cosine theta is 1 over radical 26. Exactly what you said it was up there. So this is using the identity of 1 plus the tangent squared is equal to the secant squared. Now, how do we get the sine? Oh, questions on how I did any of this? I'm sorry. Sure. So I started with this identity that seems like it's written in Greek, and it actually is. 1 plus tangent squared equals secant squared. Now, I gave you at the very beginning the tangent was 5, so I immediately replaced tangent squared with 25. I can add 1 plus 25, that's 26, and that's equal to this thing called secant squared. And if the square is 26, then that means secant is just square root of 26. But secant means 1 over the cosine, so, or cosine is 1 over secant, I should really say, from your very first. Cosine is 1 divided by secant. So cosine is 1 divided by secant, which is square root of 26. That's how we got it. Now, the sine, you could either plug it in back to this triangle to get it, but I want to show you the using these tools way to do it. I know that tangent theta equals 5. Furthermore, I know that that's equal to the sine of theta divided by the cosine of theta. Tangent sine over cosine, and that all equals 5. Furthermore, I know what I can rewrite this to say, well, sine of theta is just multiply both sides by cosine theta. So just you're solving for sine, because I want to know what sine is. 5 times cosine theta, right? 5 times cosine theta, multiply both sides. And I know what cosine theta is. It's 1 over square root of 26. So multiply that by 5, and we get that the sine of theta is 5 divided by radical 26, which is exactly what we said it was a second ago. 5 over radical 26. But what I did was I used this relationship that tangent is sine over cosine. I know what tangent is, it's 5. I solved for sine by multiplying both sides by cosine. Now, I know what you're thinking right now. It's like, oh my God, all these formulas, which one do I use when, and how do I know that's going to lead me down the golden path to an answer versus not getting one at all? And this will come with practice. You'll start seeing things and saying, okay, this is how we solve it. This is that kind of problem that I got to replace tangent with sine over cosine. And it,
I feel like the triangle is easier.
I
That
feel
was
like
way less
body
hard.
is easier.
yeah.
Like, we did that, like,
Well,
we just did the triangle in, like,
I'm going to cut this off and then just, yeah, the triangle is way easier. You're absolutely right. I'm going to go ahead and stop the recording, and then we'll just work a few problems in class. But I hope that gives those of you that are at home watching a review.